last time is we were looking at the central notion of the idea of a family, a type index. Let me write it like this. The central notion of a type indexed family of types. This is a central idea of dependent type theory. Okay, and we could write this down in various ways. For example, we can think of the family of types. Let's write this B of x, where x sort of ranges over some other type A. That's a typical sort of notation you might see that looks like conventional notation for a family of sets. So this would be a set indexed family of sets. Or as we'll tend to write this, we'll say, given x in A, we'll say that B. Sometimes I'll emphasize that there's an x there or not according to the situation, but it's a family of types. And we can think of this as a kind of mapping. We can think of this as something that assigns to each m in A, it turns it into its substitution instance, which is a particular type. Okay, so this is going to be a type. So it sends every element of A to a type. And moreover, this principle of of respect for equality or functionality says if we have, let's call it m and n, if we have equal index elements, at least definitionally equal index elements, then those should induce definitionally equal types. Okay, so this is, so these would be equal as types. And this notion, this idea of respect for equality here, is called functionality. As a typical term for this. It's the idea that the relationship is functional, meaning that it sends equal arguments to equal results. Okay, or another way of saying it is, we cannot formulate a family of types that distinguishes between definitionally equivalent indices. Okay, that's another way of saying it. So, so if I had, for example, a family of types, we talked last time about, this is not working too well. We talked, see whether that works. Get this out of the way. We talk about a family of types like, one thing might be the sequences of length n. So let's say if we have the natural numbers, then I might talk about the sequences of length n. The sequences, let's say, of natural numbers, just to be like as minimalistic about this as I can think of. So this might be a family of types. And so we're expecting, for example, based on our preceding discussion, that we would say that the types, a sequence of length 2 plus 2 would be the same type as a sequence of length 1 plus 3, maybe. Okay? That would be the same. And in particular, they classify the same terms. Okay, so therefore they classify the same terms. Okay, so that's an example. So that's the notion of what functionality is all about. So there's this respect for equality. So what we see here is in order to even get this discussion going and to talk about these things, I needed to have a variety of notions, okay? And the notions I needed are, I have the notion of a context. I have the notion of a type in a context. So this is for the sake of the induction, by which I mean we can have iterated dependencies. So for example, I could have, given a family of types B like this, I could then talk about a doubly indexed family of types, and then just to be emphatic, I can put an X here to indicate that this is dependent. And I can have C with X and Y being a type, and that would be a doubly indexed family of types. So it's indexed by elements of A and then by elements of B for that element of A, okay, so that it's iterated in this manner and so forth. So for the sake of the induction, we have in general a context, all right, a bunch of variables here, and we have types that are dependent on those variables. So this is the idea of a family of types. And then we have the classification of terms of a particular type looking like this. And then correspondingly, we needed notions of definitional equality. And our starting point was definitional equality of elements of a type. So I motivated the whole discussion by saying, well, even when we have only, when we don't have dependent types, when we have only simple types that without any dependency, it's nevertheless interesting to talk about the equivalences between proofs of a particular type, but that this concept becomes particularly significant as soon as we allow dependency for the very reason of the principles that I was mentioning here. So that then induces notions of definitional equality of types. Sometimes I'll write type here and sometimes I won't. Okay, and then that in itself, point-wise, it induces a notion of definitional equivalence of contexts. Okay, so we have kind of the formations and the equivalences written like this. Now, when people study formalisms for type theory, they'll often play subtle little games and tricks with these things to economize on the formulation. So I would rather not do that here because it can be mathematically handy to do that, but it's pedagogically not very helpful. Because, for example, you could think of membership as being defined by the reflexive instance of equality, and then you can kind of get away with only defining equality, but that's a little like too clever by half sort of thing. And so I'll just sort of stick with, a more, I think, intuitively clear formulation, even though I admit that certain kinds of economies can be introduced, and people do them do introduce them in the literature, usually for meta-theoretic reasons. Okay, so that's the basic setup, and the kind of thing that you should keep in mind for the time being at the moment is the notion of like a family of types, like for example the sequences of numbers of a specified length, or other such or various things like relations, things that come up as predicates or relations. So for example, writing mn in the natural numbers, we could have some idea of equality of m and n, which I will come back to in more detail later, which would be a type. And the way to think of that is it's the type of proofs that m and n are equal. Now, in the case of the natural numbers, because we tend to think of the natural numbers in the terminology I will use, we tend to think of them as a set, meaning that the elements are discrete. They're just sort of points, isolated points in this space, if you like to think of it that way. And so what's going to happen is the types that are being considered here are basically either empty or contain one element. That is, the fact that they're equal is an instance of reflexivity, and if they're different, then they're different and there's no element of that type. But it's nevertheless important to think in terms of it's the type of proofs that they're equal, even in the cases where the proofs may be non-trivial, or maybe trivial. In this case, they may be quite trivial. But even so, we want to think of that as the type of its proofs. And there could be other things. There could be proofs of other relationships less than or equal to, and so on. So in general, this sort of thing represents a kind of, you can think of it simultaneously as a relation, or as a predicate, or as a family of types, or as I mentioned before, as a fibration, as this kind of other sort of structure where you think of this as being some kind of big disjoint union of all. You take all of for each x in A, you sort of union up all the little b sub a's, and then you look at the things that are over a particular A. So if you just use some set theoretic notation, if you form like some sort of big disjoint union, sorry about the pen, where A is in A over B sub A, right? So there's this big fat union, we'll call that B, right? And we'll define that. Then there's a natural projection, P, which goes down onto A. And what it does is for each element in this big disjoint union, it tells you which A does it sit over, okay? The projection is over which A is it. So if I give you an element of the big clump, right, the so-called total space. Sorry, can someone help me with the pen here? This is not working out very well. Okay. So if you take what is called the total space, then this P, this projection here, is telling us over which element we sit, because you can think of these elements of this disjoint union as being like A and B, where B is in B sub A. And then, as I mentioned last time, if you look at the inverse image, if you take any particular A and you look at where it is sent under the preimage of this projection, preimage of A, that can be thought of as what is called a fiber, okay, in the total space. So these are all the elements lined up here vertically. We write them vertically like this, which are the ones that project down by P onto A, onto a given A. And for each choice of A, there's another fiber. So there's a fiber over A prime, and there's the fiber over A double prime. And that was the description we gave last time. So these are kind of two different ways of looking at. So this is the sort of fibered viewpoint, okay? And this is a kind of functional viewpoint, to think of it as a family as a kind of function, a mapping that sends elements of a type to the class of types. And this, you can think of a family of types instead as a special sort of mapping P, which is called a fibration. I won't right now indicate what the exact definition of a fibration is, but you can think of it as this kind of a projection of this style. It's a good rule of thumb, like how to think about it. And then that way, the elements of the particular thing are given by the preimages here. Okay, so that's the framework that we're working in. And then what we do with this stuff is we close it up. I mean, the reason we're interested in families of types is, remember, the things we sort of start with, right? So what did we start with? So the types we started with were motivated by logic. So we had 1, 0, and, or you know, cross and plus, however you look at it, implication, function space. Okay, so if I want to make my notation be reasonably consistent, we can write it like this, okay? So we started out with those things, okay? Then we observed that we could add additional types. There are things that are not motivated by logic, so they would sort of go on this line. So maybe the natural numbers would be 1, and so on. And then maybe other sorts of types might go in here for, let's just say, the natural numbers for the time being. I'll throw in some other things in a minute, which don't correspond. They don't have a logical correspondence. They're merely types. And this is the reason why people kind of think of the whole subject as being really type theory, and logic is just a mode of use of type theory, which is Brouwer's dictum about a logic being a branch of mathematics. That's the way he would say it, rather than the other way around. Okay, so that's the idea. And so we started with that basic notion. So now what we want to do is start populating it with other interesting types. And the first ones I'm going to do are well, we looked at little things like sequence. So we'll have various like sequences of length n, where it's understood from this notation somehow I have to indicate that this is ranging over n. And then I could have other things like equalities. We were talking about equalities over the natural numbers. So these are forms of types, okay, that can go in along here. And those can be thought of as kind of base types, right? They can be thought of as they don't have any further structure. They're just types that I'm building in, like the type of proofs of equations, the type of finite sequences. Okay, maybe this could really be represented in some other way. I'll show how to do that in a minute, but for the moment we'll take that as a primitive notion. We can think of it as a primitive notion. And then what we want to do is have some closure conditions. In other words, the whole reason for getting into this business about having families is to be able to do something with them. And the main thing that we want to do are what are called forming the general product and sum. So what we have here, there are various notations, but pi x in AB, and I'll write sigma x in AB. So they're sometimes called pi types, sigma types, they're called product types, sum types, this is sometimes called dependent function type, this is sometimes called dependent product type, which is very confusing because that in certain situations can be called a product, but in other situations that can be called a product, and that gets messy, okay? So it's again, there are terminological traditions that collided with one another, okay? Now, special cases of this include, if we go back to the logic side here, universal quantification over a type, and I'll write here P or something. I'll just write B, okay? And the idea here of existential quantification over a type. But we have to be a little bit careful, okay? These are the kind of logical correspondences. Those are correct. But you must be a little bit careful because traditionally, like for example, in first order arithmetic, you consider something much more restrictive than that. We don't consider it over any type. We consider it, for example, in arithmetic, we consider only quantification over the natural numbers. And we fix that. There's a quantifier that is dedicated to that purpose, quantification over the natural numbers. But more generally, then one can generalize that and consider quantification over other types, A. And in particular, it starts to quickly gets outside the realm of first-order logic or conventional first-order logic when we start admitting, for example, function types, because then we can talk about quantification over functions, and we can talk about for every f from n to n, and exists an f from n to n, which is outside the realm of what you usually consider in like first-order logic. Okay? So they are like the first-order quantifiers, but they're not exactly. They're a bit more generalized. But that is the kind of analogy, and I'll explain why that's a good analogy by telling you what the rules are for forming the sigma and the pi. There's going to be another issue about the behavior of existential quantification that will come up here as well that is known to be problematic. So these kind of correspondences have to be taken somewhat with a grain of salt because there are many complicating issues to be discussed. Okay, so what I want to then do here is to start populating our type theory now, be more serious about it, and formulate what are the principles of forming these so-called dependent types. Now, I'll remind ourselves that we have a bunch of structural principles that sort of come along for free. I won't write down all of them. I've given you references to the literature where you can look up the formal definitions of the type theories and stuff, because it would be awfully dreary for me to write out several dozen rules and stuff and everyone would go to sleep. So I'm just going to point out the main things that are important. So for example, you can always use a variable at its type. Okay, so that's an example of a structural principle, the use and behavior of variables. Okay, the principle of substitution. Well, there are more or less general ways to say this, but one version of it is this. It says if x delta gives us, well, now the question is what goes on the right. So I'll cheat here and I'll write a judgment j, and you'll see what I'm going to do here in a minute. And it says if I have an m which is of type A, then in the instance, remember these can be sequentially dependent, so I can plug those into delta, and then I can plug that mx in for j. Well, I'm a little cheating here because j stands for any of these judgments, right? So it could be a typing judgment, or it could be a type formation judgment, so I'm using a Blackboard economy here to explain these things concisely, but really I mean a bunch of rules here, one for each choice of those judgment j. But this is the principle of substitution. So these are the fundamental ideas about variables, right? That a variable is an unknown element of a type, and you can give meaning to variables by substitution, by plugging in for them. That's what variables are and what they're for. This is how we do it. The principles of functionality say every judgment is going to be functional in those in its free variables. So here I have to actually write this out. There's no easy way to write this out other than directly. So let's write let's say n colon b here, and if we have equal elements, oh, I shouldn't have called it m, and well, let me just call them m and m prime, okay, like that. Then we're going to want to know, well, there's various things we're going to want to know. Let's look at a specific instance. Let's just look at the last variable. The technicalities are technicalities. The thing I want to get in here is that m for xn should be equal to m prime for xn in m for xb. Excuse me for squeezing, that goes there. And the point being, by a similar rule, which I won't write down, equal instances will give us equal types, so the fact that I chose m for xb here is immaterial because that's going to be definitionally equal to m prime for xb in the way in which we spoke before. Other structural rules come into play. There are rules for weakening, okay, which I won't write out here. We talked about it last time. Contraction, exchange.
Is substitution something that actually needs to be included as a rule, or is it going to be admissible?
Well, I'm assuming I've defined it for all. I haven't really given that definition to you. It's
right, I mean, but the substitution rule you wrote up, does that need to be included as an inference rule, or is that?
So this is what I am not doing, okay? What I'm not doing is committing to some specific formalism. I'm trying to give you the semantic principles that are going on. And then because of various considerations of meta theory, people formulate it in different ways. That's what I was saying before. There are many different formulations, no one of which is right or canonical or best or anything. There are just different ways of doing it. So what I'm trying to do for the purpose of teaching is to give you the ideas, and I'm not committing to like, this is a rule and that's not a rule, and this is admissible and that's not admissible. I'm not going to worry about that because I'm not going to be doing any meta theory. If I were doing some meta theory, then I would have to be very extra careful because I'm trying to cross all my T's and dot my I's. So I'm being a little loose. I admit that I'm being loose, but there are I'm being faithful to the truth, and you can look in the references I've given you for the various forms of the story. Okay, so we'll have weakening, we'll have contraction, we'll have exchange. I won't bother to write them down as rules, but those should be valid principles in one way or another. Either they're admissible rules or you put them in explicitly, and let's not discuss why you do one or the other, but let's say we're going to do this. And then I mentioned last time, amongst many other things, there's the respect for equivalence as well, which says definitionally equal types classify the same terms, and etc. Like equal things of this type will be equal at that type, and so forth. So I'll just write etc. here because I don't want to. It's really too boring to write down every single thing. Okay, so that's the flame. But the point I want to say here is that these are the structural principles, right? This is what makes the theory work. This is the generic stuff, and mostly it's about the behavior of variables and the notion of definitional equality. So in particular, whenever you have an open term, whenever you have some form of, like if this is a typing judgment or it's a type, whenever you have some open judgment here that has some free variables, the rule of thumb is it's a mapping that is functional in those free variables. Okay, that is the idea. We're worried about the pen? I really dislike whiteboards, but you can't teach properly without chalk. Thanks. But all right. So these are the structural principles, and they are primarily about the behavior of variables. That's essentially what is going on. And so so we have those. Those are like inherited. Those are for those are the context in which we're working because they define for us what we mean by family. Okay, this idea of functional dependency. Okay, now the other thing I would like to say is that there's another way of looking at this. It's the same thing, but you could also look at it this way, which is the origin of the notion of type, which goes back to Russell and Whitehead's work, is that a type is the range of significance of a variable. That's another way of looking at it. Okay, whenever you have a variable, you must implicitly or explicitly specify what does it range over. And the thing that it ranges over is called a type. That's the notion of a type. Okay, so in school, way back when, all of the variables ranged over the real numbers. Okay, and nobody ever, I mean, that was clearly specified, but you don't really write it down because everything is tacitly ranging over the real numbers. So here we're going to be, specifying specifically what the range of significance of a variable is. So there's a kind of like general rule of thumb. Whenever you have variables, you have to have types because they go together. It is the range of significance of that variable, and you must specify its range of significance. So that's why all these things kind of fit together in the way that they do. Okay, good. So that's the general framework. And now what I would like to do is start, instantiating this a little bit. Okay, so I can say a few things. All right, so let's look at the behavior of the quantifiers. And I'm just going to dive in and do them as type constructors, and then I'll draw the analogies to logic on the fly. I could, in fact, continue this whole discussion I was giving you before, but carrying it out in parallel starts to get complicated. So now I'm going to just do like type theory, okay? And then I'll make the analogies to types to logic. And Steve, I think, will talk about the connections with category theory. The connections to categories are, at this point when you have quantification, start to become more involved. And it's a little hard for me to do that just on the fly. So it'll be nice to set Steve up for doing that. Okay, so let's look at, for example, the product. So this is the, like, in some way where all the action is. So we are going to, admittedly, I'm starting in the middle. I will piece everything together in due course, but I think it's best to do it like this. So what I'm going to do is I'm going to say, under what conditions is that a type? Well, the conditions under which it's a type are that A is a type, well, really, under which it's a family of types indexed by gamma. okay? Because in the induction, that's what we always consider. We only ever consider families. If this happens to be empty, okay, that's fine. Then it's a closed type. Yeah. There's nothing I can do here.
Find you a better one.
Okay. I mean, I'm doing my best.
Keep going with this one for now.
Okay. All right. So everything is to be thought of as a family of types indexed by gamma. We'll carry that along. So A will be a type, well, relative to gamma. So of course, it's going to be a family of types. And then there's an additional level of variation where we say B has to be a family of types indexed by A. So it'll be written like that. Okay? So if you hold the gamma fixed for a moment, like you could think of it as like a currying, instantiate gamma however you like, fix that instance, then that's orange. Yeah. Okay. All right. All right, I'll put that in my back pocket. Okay. All right, so you fix the gamma and you say, okay, then what I have is, for the fixed gamma, I have a type and a family of types indexed by the elements of A. So that's, and this is called the big Cartesian product. So this is called the pi formation rule. A lot of times it's written like that. So if you look at this by analogy, if you think of this now as from the point of view of logic, what I would kind of pencil in here, maybe that's what orange is good for, what I would pencil in here is this would be a proposition, and this would be a proposition. But if you're thinking of it as logic, that would remain being a type. In other words, conventionally in logic, and this is partly where it's better to do type theory than it is to try to relate everything to logic, because in certain dimensions, logic has remained degenerate in ways that it's not when it's presented from the point of view of type theory. And one of those dimensions is, in logic, you don't normally, in conventional textbook logic that you look up, one never considers quantification over propositions because proofs are not mathematical objects. That's completely out of the game. So you have a notion of type, which is your domains of quantification, okay? And then you can form propositions or predicates over a particular type. And in certain really degenerate forms of logic, there's only one type ever. Okay, maybe it's a type of natural numbers, possibly. There's only one type, but there could be many. If you have, then it's called multi-sorted for some reason. Okay, and then you have a notion of a proposition indexed by that type. But in the context of type theory, we just say, oh, props types, that's just like a matter of your point of view. Okay, there's no real difference between a proposition and a type. They're the same thing. So that has some consequences. It means, in particular, that the thing we're quantifying over could very well look more like a proposition, really. Okay, I mean, it's a matter of how you look at it, of course, but it could have the form, involving only logical connectives, and then it looks like you're quantifying over proofs. And the reason being, proofs are mathematical objects, just like all the others. Types classify all the mathematical objects, and that's what we quantify over. So, en passant, we get proof quantification over proofs. So it all sort of works out smoothly. The conventional story is a bit, thanks. The conventional story is a bit contrived when you see it from a type theoretic point of view, because type theory was the first sort of comprehensive understanding of logic, in my opinion. Okay, so but that's what it would look like, and then you would tend to write, if it were a logic book, then you would tend to write this as for all. So you would make the distinction that that's a type, this is a proposition, and then you'd write that as a for all. Okay, so that's a special case of the general thing. All right, and then continuing in the pattern of natural deduction, then we have to decide what are the elements of this type. So let's look at the introduction. All right, so let's think about this. So I want to say something or other is an element of this type. I'm also going to have to say equality and stuff, but I'll get to that. Pi x and AB. Okay. So if you just think of your set theoretic experience, then if I look at, you may well have seen, I'll jot it up here on the side, the idea of pi x in A, B of x, where this is a family of types indexed by A. That's what we're describing. And this is variously described as being in infinitary sequences, like that is A indexed elements, so it's basically B sub A prime, B sub A double prime, etc., for each possible choice of A prime. People sometimes write it like that. Or there are various ways you can notate it. Okay, well, really what's going on is it's a function, it's a mapping, that assigns to every element of here an element of the corresponding instance here. So the way we're going to write that is as, well, given an element of the domain of quantification, I expect you to give me, and let me put a little x here just to indicate, a variable element of the variable type. Okay, so this is an element that knows about x, and this is a type that knows about x. Okay, and then the idea is, what you're saying here is, this is a mapping, right? This is a mapping that assigns to each element little a in A. It assigns m sub a, which is of type b sub a. And the collection of all of those forms, if I put those all together, that will give me an element here, and that's a lambda abstraction. So this will be written lambda xa. If I wanted to emphasize, I could write m sub x. Okay, and then in that case, I would write b sub x, and it would look like that. So that's the pi introduction rule. So the point is it's a function, and this could also be notated send x in A to m sub x. You could write it like that. Or you could write it as, angle brackets m sub x in A. I mean, there are various ways of, people notate it, but computer scientists use lambda, of course. So we'll write it using a lambda. Okay, so that's the introductory form. And then the elimination form, and this is a characteristic thing. Yep. Everything written where now?
On the top of the board.
At the top of the lower board? Yeah, so what I was trying to do is I was trying to give us a little chart. We could write this in 2 columns if we want, 2 rows if we want. So we started out with various propositions, and then we drew analogies between those propositions and types, and then we got carried away and started writing down a lot of types that didn't correspond to proposition, and then they kind of do again in the way that I have been explaining. That's not, the correspondences to traditional things are not exact, because traditional things are weirdly incomplete from the point of view of type theory. Did that answer your question? As one what? Because they're not. I mean, because certain types do not correspond to propositions, and certain accounts of propositions, like you find in books, are only fragments of the types.
I mean, at least the ones that correspond to something. So, like for all, why do you insist to write pi instead of for all?
Oh, why do I use that notation, you're saying? As I say, because the quantifiers all only exist, it's a notational tradition. I mean, it's a basic thing I can tell you. I want to emphasize the idea, the constructive content of propositions as being, a proposition is nothing other than the type of a bunch of proofs. And so by writing it in this kind of notation of pi and sigma stresses the idea that it's a construction. Yep.
Propositions are a subset of the types, right?
Is they?
Are a subset of the types, is that what you're saying?
Yes. Okay, I don't know what further, how much further I can take it.
I'm just not sure. I'm not sure whether it's trying to stress that there's a difference that I don't see, or whether it's just.
No, it's there are, as I've mentioned, there's a collision of terminology and notations that have arisen over a century or more, and I'm trying to make clear the correspondences. But what I really care about in my heart of hearts is type theory. And so I'm writing down, type theory and then trying to draw the analogies as much as I can. That's the best I can do for you. Believe me, there are some really horrendous notational collisions that you'll run into that can be very confusing. Okay, what now? Okay, that seems to work. Okay, so yeah, that's the best. I mean, if it's not helpful, well, I'm sorry. I'm just trying to be helpful. So I don't know. Okay, so going on, we want to look at the elimination forms. So we want to say, what do we do with an element of this? If I have an element of pi x in A, B, what do you do with that guy? Well, remember, it's to be thought of as perhaps as a function or an infinite sequence or whichever of these kind of notations you like to think. So what I can do is I can instantiate it, and by instantiating it, I instantiate it at a particular element of its domain. So what I do is I say, if you give me a particular element of the domain, then, okay, I need a notation, and typically it's just application, that you take the nth element, as it were, of the sequence m. That's a way to think about it. Or you can think of it as applying the function m to the argument n. It doesn't matter. And what you get back is a corresponding instance of that family. And this is the critical idea here that goes on, is the fact that when you choose from this sequence a particular thing, n, and you plug that in, the thing you get is in that fiber. Okay, so it's here. That's where this belongs. And that's a characteristic feature. And then if we look again at those principles of definitional equality that I talked about so far, then we will get that the baseline understanding, you recall, is the idea of computation, these beta-like rules, which are representing what Frank, I think, probably called the inversion principle, the idea that the elimination rules invert the introduction rules. So it says, if I take something which I have explicitly introduced, so let's write it like that, and I then eliminate it, do it in application, that should be the same as just plugging in this case, n for x in M, and its type will be n for x in B, under suitable premises like A is a type, and M is a family of elements of the family of types B, okay, like that. And this is the sort of beta-like rule, and this can also be called pi computation, if you will. All right, so that's like one of the basic principles of definitional equivalence. Now, I know that it has come up in Frank's discussion whether there should be other principles of definitional equality. And for the time being, I'm just not going to go there, okay? There is some, I said to you before, the exact idea of what is definitional equality is a little bit up for grabs. It's not completely clear. I think that Frank might have postulated for you a different rule, which I won't officially take because I have other ways of dealing with this, but one might consider as well. I'll just put a question mark, a rule that says, the other way around. This is the local soundness, so it's what Frank calls a local completeness. So if you put the intro after the elim, that somehow should also be a no-op, right? That those should cancel. And I'll just leave that. That's called the ETA rule. I will leave that aside for the time being. I certainly demand, at a minimum, the beta-like rules, which is consistent with the idea that definitional equality should be representing equational deduction as a consequence of the definitions or just symbolic execution. Okay? So if we take that as our baseline understanding of definitional equivalence, certainly we want that. And this somehow is a different sort of thing. This is a kind of an induction principle. It says every element of the type is the form of a lambda. So in the same way that like mathematical induction says every element of the natural numbers has the form of either a zero or a successor. It's a little bit like that. So I kind of don't want to, I probably don't really want to go there and introduce this as a principle of definitional equality, okay? However, I will admit it's not like hard and fast rules here. This is like, I'm giving you some feeling, okay? All right, so that's the notion of the product, okay? And you can see, by the way, that this, I should have said this before, this corresponds a little bit to the rules that you would expect to see for like universal quantification. Because, well, in traditional logic, you don't worry too much about the forms of proofs. But if we said B of x is true for every x in A, so suppress this and just read that as B of x is true for every x in A, then something or other which we suppress in the traditional accounts of logic witnesses that for every x in A, B of x is true. In other words, the meaning is just exactly that it's true uniformly in x. And then that looks exactly like a conventional rule of logic when written like that. And the same here, if we read that as for every x in A, B is true. So if we read that, forget the M itself and just worry about the fact that it exists. if this is true and I have a particular element of the domain, then, well, in traditional logic, we don't worry about how to notate it, but what we get is the fact that n for xb is true. That is, if I quantify over x and I plug in a particular x, then that instance is true. And the truth of it is witnessed by this application. Okay? And then in traditional logic, because we don't worry about proofs as being objects of study, then we don't worry about when they're equal either, so none of this comes up. Okay, it's a pity, but that's the way it is. Okay, so once you learn logic from the point of view of type theory, you'll never be able to look at logic the same way again, because it will look very kind of broken to you, because somehow half the story has been completely omitted for some unknown reason. You know, that's the way it is. That's part of the advance of type theory, why it's important, why type theory is important, and has made advances in the field that have not been made before. So it doesn't erase very well either. Okay. All right. So that's that. So now let's also look at the sigma type, which is you know, looks sort of formally similar. So the idea is this is a big sum. So we're going to say we have the sum over A of a family of types B of X. I'll write that here. And that's going to be a type exactly when A is a type. So you have a domain of quantification, and B is a type. So the formation conditions are the same. So this is sigma formation. Okay, and then we're going to have the introduction and the elimination. Okay, so the introduction is, what does it mean to have an element of sigma x in a B? And I can write the x there if I want, just to emphasize the dependence. Okay, so what is an element? Well, this is supposed to be thought of as the big disjoint union indexed by A. Okay, so it's the big sum over the type A of each of the elements of type B of X. So the elements of that type can be thought of as consisting of an index element A, say, hey, I'm over, this is the particular element of A I'm talking about, and an element N whose type is M for XB. And in that case, the pair Mn becomes an element of sigma, the sum of sigma x and AB. And this is where another terminological confusion comes up, because the elements of the sum are pairs. So then people say, oh, so we should call this the dependent product after all, because it's a lot like product, except that it's dependent. And that's true, but it's confusing. Okay, so it's the terminology doesn't is a long-standing issue here about the terminology, but I'll just explain to you what that is. So if we're taking this big disjoint union of a bunch of things, if we think temporarily of these as sets, it's misleading. The set theoretic interpretation here is low dimensional, and we're going to be talking about higher dimensional interpretation later. But in the low dimensional setting, these are just sets, so this is a big disjoint union of a family of sets indexed by a set. So these are just the formal notation we have for writing down the elements of that union. So now I want to say that this corresponds, and again, the correspondence, it's a little awkward because it doesn't line up with some textbook exactly, and I'll tell you why in a minute. But it sort of corresponds to an existential quantification, right? It's going to be the idea that, and you can see this nicely when you look at, this is called the sigma introduction rule. If you think of this as an existential quantifier, it says, if I want to show you that there exists an x in A such that B of X is true, then what I do is I exhibit a particular A, that's the witness to the existential, and then I tell you that that particular instance, that B is true for that particular instance. And so you can see the correspondence to existential quantification. In ordinary logic, as I say, the proof objects are suppressed. So the only thing you see is the term, the particular witness. So if you're working in arithmetic, that would be a number or something. And then you would show that that instance of B is true by the rules of logic, and then you would conclude that there exists one. Okay? So that's where that corresponds. Of course, the correspondence starts to break down as soon as you realize, as I mentioned again, to reiterate, in type theory, A can range over more things. Now, the correspondence starts to really break in the next rule. next two rules, which are the sigma elim, which I'll 1, and sigma elim 2, and then I'm going to give you an assignment. Okay. All right. So this is what we do here. So what I want to do is I want to invert, okay, the introductory rules. I want to say, well, if you give me an element of the sigma type, you write it like that, what can I do with that guy? Well, the principle of it is that the introduction rule tells us what the elements are. They're ordered pairs. So if I put two things into it, then by the principle of conservation of proof, I should be able to pull those two things back out of it. Okay, that's the idea. So this is so I put M is something that I put into it. We know that ultimately what I put into it must be in this form, so we'll introduce projections. So there are different notations people use. One is pi 1 of M, which is A, and then under the same conditions, put here pi x in A dx, and then we will have that pi 2 of M is, and now this is the critical thing, pi 1 for M x B. That's very critical. Okay, so, and then we would have definitional equivalence rules, and if you don't mind me slightly just scribbling, I won't write it all out carefully. It's the obvious ones, that this should be M and this should be N. And as an aside, the converse of the local completeness would say, if you do this, you should have M, but I won't consider that here as a principle of definitional equivalence. I won't do that, but that's a similar analogy to what we had before. So this is these are the important ones for computation. Okay, now the question is how this looks compared to ordinary logic. And the answer is it doesn't look very good compared to ordinary logic. And this is a spot where the way I like to see it, oh yeah.
Is this like the traditional way of doing it, or is it possible or ever done to write it the separate way, like the CDS version where you say, like, let...
That's what I'm about to say.
Okay, cool.
Okay. Second. Okay. So here's a collision point. So for me, okay, I'll tell you my point of view. The logic can only be explained as a mode of use of type theory, period. Okay? But people have tried to explain it without the benefit of type theory, and you get into trouble. And this is a spot where you get into trouble, and I'll tell you why. Okay? So suppose we think of this as an existential quantifier. Okay? So if this existential formula is true, that's the way we're supposed to think about it, well, one thing you've got now is a term. A term that takes a proof and turns it into an object of the domain of quantification. So at the moment, let's say, just for concreteness, let's think of A as being the natural numbers. Then what you're doing is you're saying, give me a proof of exists X in A such that B of X, and I'll extract from that proof a term, a number. You can't do that in ordinary conventional logic because the proofs are not objects. Okay, you're not able to even express, this is a non-starter, there's no way to even say this. So this does not correspond to a rule in conventional logic. And this one is only worse. If you make this into an existential quantifier so that what you're doing is you're saying, well, the M colon means this proposition is true, then you're able to extract from it another proof, which is a proof that the quantified formula is true for that particular witness, pi 1 of M. I don't know what pi 1 of M is. For example, M could be a variable. So I don't know what M is. M is not necessarily a tuple that I know. It could be a variable. But certainly pi 1 of X is an element of A such that this formula is true. That cannot be expressed in ordinary logic either, right? There's no way to say these do not correspond exactly. Now, I would argue that these are the correct rules for existential quantification. I need a spot in which to write. I'll go over here. Okay. But they're not the ones you usually get. So what are the ones you usually get? And I'm going to ask you to derive them. The ones you usually get is something that looks like this. It says, well, let's write it as if it were type theory, so we'll do it like this. So if you have an element of sigma x in A, B of x, or think of that as an existential. So if you know that the existential is true, then you reason as follows. You say, well, given x in A, given a proof that B holds for that particular x, because the way you reason is you say, if I know that there exists a number with a certain property, I say, well, let x be a number with that property. And the with that property part means introduce a variable standing for the proof, okay, that you have when you're working in the constructive setting. And then you derive a proof of some other proposition. Okay, this is the typical thing where that proposition is extrinsically meaningful in the ambient context gamma. And then you say, something or other witnesses the truth of C. And it's a kind of let. There are many ways to write this, but it amounts to something like let x, y be m in n. N, that should have said, excuse me. All right, in n. Okay, it would be like that. That would be your typical, suppressing the proof objects, that would be your typical mode of reasoning in a typical formulation of logic. Your exercise is to show that that's derivable. Okay, so we'll do it like that. So you can get it on the basis of these principles. But these principles are, much stronger. I mean, these are saying, well, they're saying the right thing, okay? First order logic or conventional treatments of logic like this have to talk around it because they have no way. This object here is an alien beast. That's as alien could be because you're making a number out of a proof. And what's a proof? Okay, you see? And because of that, okay, that is a very important concept which I'm now going to exploit by giving you a little example. Okay, so that's what I'm going to do. All right, so that's the rule. So let me use these two rules to show you something about quantification that I think is important. Okay, are you with me so far? Is this okay? Okay. All right, so let me roll that up. So now I want to talk about something, and this is the traditionally at this moment is the right thing to talk about. I'll talk about something called, I'll put it in quotes, the axiom of choice. Okay? And actually what it is the theorem of choice. Okay? And that's what I'm going to do. Okay? There are many ways to formulate what in like traditional. So what I'm going to do is I'm going to portray this to you in a form that makes the traditional accounts look bad because I think the traditional accounts are bad. Okay? So I will explain it to you as follows. Okay? So the traditional account of the axiom of choice, there are many equivalent formulations of the axiom. I'm sure that you could rattle off a dozen of them if you want. But a very basic one is every total relation, binary relation, contains a function. Okay? So how do you say that? So one way to say it is you say every total binary relation, that's I'll write it out sort of in English, contains a function. So what does that mean? If I have a binary relation R, which is total, that is, whatever its domain is, every x is related to some y. Okay? It's total. I'm going to select from that R a subset, which is going to be a function. So I can write it out like this. So what you say is, okay, if for every x, let's look over a relation over A and B. So if for every x in A, we'll write it like that, there exists a y in B such that Rxy, that's totality. Okay? That's how you would write it out, like in logical notation, right? The relation R is total means for every x in R is relation between A and B. So between for every x in A, y, yeah. Then I do this all the time. Then there exists a y that is related to it by R. That's what totality is. And what you do is the so-called axiom of choice says this implies that there's a choice function. That is, a function which witnesses the totality of that relation, which can be expressed as saying, well, the simplest possible way, I can actually jazz this up a little bit, but the simplest formulation is you look like this, that there exists an f, such that for every x in A, I choose the y, f is the choice function, which chooses the y. So this is called the choice function. okay, which chooses the y that corresponds to x in the relation R. Okay, so that's what it would be stated as a principle of logic. Say again? Did I make a mistake again? F of x, yeah, jeez. God, I'm really terrible with that. Yeah. Okay, yep. Sorry. Okay, so that's the way. So the statement is sensible, I hope. Okay. Notice, in order to say it, I needed to have existential quantification over functions, because I have to have a choice function is a function, so I have to be able to express that. Okay. So a lot of times this is formulated in set theory, where there's really only one type. It's the type of sets. Okay, and then you work everything inside that one type, and it's a kind of cockamamie way to do things, but it's what you do. Okay, that's the way it's done in set theory. It enjoys all of the deficiencies of any unityped approach to programming or to doing mathematics. You have a lot of codings, and it's really unpleasant. Okay, so the idea about type theory is to just bring out the structure which is there rather than try to hide it. Okay, so here I do that. I bring out the structure that's there by being explicit about the typing. Okay, so I have this. So as you very well know, no matter how the variations of how you formulate this, this is postulated as an axiom of, for example, set theory. Okay, and it's known that it has to be postulated as an axiom by a very complicated argument, which says that it's independent of all of the other axioms of set theory. So you really have to, postulate it outright. But it's a weird thing and people find it questionable because it has existential force, right? It tells us that certain things exist which, so to speak, otherwise don't exist. In other words, if you write down the words, the rules of set theory, and you have a notion of function that arises from the idea of power set and da-da-da-da, and you write it all down and everything looks really good to you, and then you suddenly realize that you've missed some important functions. And so the way you do it in set theory is you say, oh, the hell with it. You just postulate it outright, of whole cloth. You just say, we'll throw that one in there too. Okay? And that's the axiom of choice. That's what you do. Well, that's what people do. And it works for some value. It works. So the thing I want to point out here is that in the constructive setting, it doesn't need to be an axiom. It's actually a theorem. And I think it's helpful. This is a person that's What I'm going to do next is a purely psychological move that may be helpful or not helpful, which is to think of this as a construction inside of type theory. So it says, I'm going to write down a function that is given an element of the big disjoint union. And what you want to do is you want to think it like this, okay? So it's given this construction. It's given an element of this disjoint union as an argument. Okay? And then it wants to deliver back, it wants to produce an element of this disjoint union. Now, all I'm doing is changing the notation. I am, but I'm trying to stress the constructive reading of this. That's why I'm doing that. Okay? If you don't like it, then just ignore this line. It's the same as the previous one. Okay. All right. Oh, did I screw it up again? What did I do now? Too many people talking at once. Oh yeah, that's a pi x in A. Sigma, yeah. It's weird, I'll tell you, it's hard to get these things right when you're up at the board. Okay, so that's a restatement of what I'm going to do. So what I'm going to do is I'm going to say, I'm going to show you there exists a term m, okay? And I'm going to tell you what that term is, okay? And therefore I'm going to give you a proof, okay, that this is a theorem. That's what I'm doing. So how do I do that? What I'm going to do is I'm going to define m in sort of the only way you possibly can. So what you do is you say, okay, I'm going to take in as an argument a proof, let's call it T, just because that's what I happen to think of, a proof T that a relation is total. You see, I get the proof as argument. See, that's what's really slick and clever about all of this, okay? Look, you're saying to me, this implies that. When you say this implies that, it means that you have a way of transforming a proof of this into a proof of that. So what I'm going to do is I'm going to write down that code. Okay, I'm going to write down a function lambda that takes in a proof of the totality. And I want to emit, I want to get out of this thing a function. So I'm going to write down here a pair consisting of a function and a proof that works like that. So I need to write down a function here of type A arrow B. So this will be written lambda x in A, something. Okay? And then this will be a proof that for every x in A, something or other holds. So this will have to be a lambda, and then this will be something. Will get filled in here. Like, we agree that that's pretty much what you have to do, right? Is I'm going to use t in here somewhere, obviously, but this guy has to be a function, right? There's a existential quantifier here, so I got to show you the function. I'm going to write that down, and then I have to give you a proof, which is a function because it's a for all statement. It's a pi. Okay, so I can write that down. So what do I do? So, well, if you claim to me, what do I want to do? I want to say, given x and a, I want to use this information t to extract an element of b in such a way that b will be related to, that extracted element will be related to a. Okay, that's what I'm going to do. Well, that's pretty damn obvious because I'm given that for every x in a, there is a b. So what I'll do is I'll just take t, take pi 1 of t of x. Did I do that right? Okay, I think I do pi 1 of t of x. Because if I take t, which is a proof of the totality, that's why I call it t, of the relation, and I give it the particular x, it emits, right, the assumption, the proof emits a witness and a proof that it's related to x is related to that witness by r. So let's pull that back out. That's pi 1 t of x. And then what do I do over here? Well, what I do over here is I want to prove that for every x in a that they're related. Well, what do I do there? Well, that's just pi 2 of t of x if I didn't make a mistake. Why? Because the type of pi 2 of t of x, remember, is substitute pi 1 of t of x in for y in rxy, which is exactly what I want. In other words, I want r of x, pi 1 of t of x, and pi 1 of t of x is the result of applying this guy to x. And I believe I am done. Okay? And that is, if I didn't screw it up, that's a correct proof term. So this should be called the theorem of choice. Okay? And that's it. This is a very remarkable thing. What makes this work? Okay? The key is that proofs are mathematical objects. This is what I said to you in the beginning, the very beginning. Well, logic as if people matter. We start out with proofs. We treat proofs as objects in our theory that I'm able to extract. I have t of x as a proof, and I extract an object from the proof. So this is extract the witness from the proof. So what's happening in the usual formulations of the axiom of choice is you don't have access to the proof. So you're supposed to get the f out of nowhere at all. Okay? You're supposed to, the f has to magically appear for no good reason whatsoever, because there's no way to get at what that f is, because there's no way to examine the hypothesis, which is a proof. When you have the proof objects available, you just hack around with them, and it becomes a theorem. So the theory is completely self-sufficient and self-contained and works for general reasons. It doesn't require any kludges, okay, to make it work. I sort of view the axiom of choice in sets as a kludge. Okay, that's what's happening. You wrote a whole bunch of code and you erected this big apparatus, and then something doesn't work, so you kludge in a little fix. Okay, so that's what you do. So it's kludge. So here, it's not. It works for general reasons. So another way of saying this is, which is implicit in what I'm saying, is the only way in a constructive setting to prove, and this is a little more subtle, I hope I can get this across. Another way of interpreting what's going on here is the only way to prove the totality of a relation in a constructive setting is to exhibit a function. Why? Let's see if I can tell you why. In other words, what I'm really saying here is implicit in the proof of totality is a function. And I'm going to make that function explicit. That's what it is saying. So why is there a function implicit in the proof of totality? Exactly because the rules of quantification tell us that a proof of a universal quantifier has to be functional in x. Why? Because here you're going to give me a proof uniformly in X, and by the principles of structural equality, this respects equality in the domain. So this defines a mapping. It's a function. So the proof has to be a function that takes X, and for any X, gives us, as a function, this ordered pair. Okay? So the point is that in order to prove for all exists, you must, when you write the proof, implicit in the argument must be a functional choice. You must have made that choice already. And all this is doing is extracting from the proof the choice you already made. Okay? So that's the critical idea. That's what's really going on. Now there's another even more beautiful idea going on, which I think Steve Audi will talk more about, is that we can interpret types as kind of topological spaces. And then what is happening with the universal quantification is a continuous dependency of the choice of the pair here as a function of X, so that this will intrinsically come out as a continuous function. There will be no discontinuities. Okay? And in fact, one of the beauties about type theory is that the type theory is set up in such a uniform and smooth way that you can consistently interpret the entire thing as speaking about continuous functions over topological spaces. And this has an enormous significance. And we'll say a little bit more about that later. But it's intrinsic in the constructivity. It's the idea, the constructive ideas that I'm explaining to you are what make that whole engine work. Okay? And it's really important to understand that. So I want to emphasize, at least here, the constructivity, and we'll get back to the continuity and topological interpretation later, and its relation to homotopy theory. We'll get to that. Okay, so questions about the so-called axiom of choice? Yes? Say again? What pi1 is doing is extracting of the existential quantifier from a proof, because T is a proof. I mean, in type theory, I've said over and over, there's no distinction between proofs and not proofs. But if we think of it, I wanted to draw you through it by thinking of it as logic. So if I think of this as logic, then T should be thought of as a proof of a pi2 sentence for all exists. Okay? And then what I'm doing is I'm writing down a term of a type. Okay? So maybe this is n arrow n. Like, think of A and B as both being the natural numbers, if you like. So I'm writing down a particular natural number that is obtained by running the projection on a proof. That whole concept is completely non-existent in first-order logic and the usual textbook accounts of logic. Look at any of them. There isn't a single one. Okay? Type theory is the only one that gives pride of place to proofs. And that is a thing of beauty. It is the most gorgeous intellectual idea that I know. And its implications are dramatic. Yes?
Sometimes I think people prefer to not have the axiom of choice in the logic.
Well, in set theory they do, but that's because of the problems of set theory. I mean,
okay, so that benefit of
the reason they don't is, typically, as far as I know, the people who sort of say don't want it, other than people doing meta theory who are like trying to relate various axioms to each other and stuff. Let's forget about that for a minute. Practice, the only reason people would say they don't want it is because it's a bald existence statement that has no justification whatsoever. Okay, you just say, there exists such a function, period. It's a kludge. I mean, it's a recognition of the fact that it's a kludge. Basically, everybody knows it's a kludge. And some people will write out, I can't get this open, and some people will write out in their papers whether they relied on that kludge or not, because they sort of feel guilty, in my opinion. It's never been comfortable, okay? But the problem is the set theoretic foundation. They don't really make much sense, okay? And in the long run, that'll all go away, okay?
Can you always extract a witness from a proof?
Yes, in the formulation I've given here, you can, because if I can find the board. This is how I axiomatize the sigma type, is that the elimination form extracts it. And I'm strongly emphasizing that this is an unusual feature of type theory. It's only possible because you're in this setting of type theory that you can even entertain the notion. That's the way to think about it here. Okay. So that's what's going on with sigma and pi types, and this is a very good example, okay, about sigma and pi. There are various ways to generalize this. You can generalize it to allowing a dependency here, in which case this would become a pi. So you can do that. That's a minor generalization. Okay, you could do that. I thought I would do something simple first of all. Okay, so that's certainly a form, and there are many equivalent reformulations of this that can be written down and proved. Okay, so good. Another thing you might do is, if you only had this as your elimination form for sigmas, you will fail in trying to give a proof of the axiom of choice. Try to do it, okay, and see why it doesn't work. Okay. Well, yes, the whole theory is constructive. I mean, well, okay, that's a little bit hard to answer, because classical logic is a mode of use of constructive logic in which I postulate as an axiom that all predicates are, all propositions are decidable. So in that sense, it's perfectly classical. It's just that when you do something in classical logic, you're using a kludge. Well, the way I would say it is a heuristic assumption. There's a heuristic assumption that it can be helpful to someone. Like I said, if you think about Newton's method is a really good algorithm, but for the fact that you can't actually compare real numbers and tell whether one is less than the other or equal to 0. Okay? So you make a heuristic assumption. You say, let's work under the convenient assumption that the real numbers are, atoms that are discrete, that we can compare and treat them like data, and now let's work under that assumption. That's what, and then the justification for Newton method is exactly that. Okay? Yes?
Something I don't know. So, is what you're saying, okay, now that we're using heuristic logic, we have witnesses for a grid. We always have a witness
Yes.
for the grid.
Yes.
And so we can use it.
Yes, that's right.
Okay, and this works, you said that only works in type theory, but I guess it also works.
No, this is type theory.
Yeah, but I guess it works in corresponding logic, right? Intuitionistic logic.
Yes, that's right.
So
Yes.
you can also prove the axiom of choice in intuitionistic logic.
If intuitionistic logic is formulated as type theory. Okay. I know you're finding it. I know. I'm trying. Okay. My explanations are partly based on the assumption that you've seen other treatments of logic. I don't know whether you have actually. Okay. If you look at the textbook treatment of even intuitionistic logic, it is not done like this. And then it's a. Okay, it doesn't work properly. What's that? You won't be able to do this. This move will not be available. Okay, so if you took a version of logic, if you tried to write down, so here's the exercise. If you tried to write down the rules for a kind of first-order logic, let's say a multi-sorted first-order logic, even a single-sorted first-order logic, where you quantify over one or more types, and you write those rules down, one of the rules you'll write down for on the left-hand board in orange. Okay, because that's what it will look like in the ordinary textbook formulation of logic. You will not be able to carry out the derivation in that formulation of logic. What's that? Because it's broken. Because it's broken. Okay? Because you cannot fully express the inversion principle. The idea is that the rules I've given here fully express the ones that are now obscured on the board, the sigma rules, are fully expressed. They invert the introductory rules. That is the proper expression.
You're saying that the elimination rules that we use
Are broken.
Are not complete.
Yes, they're broken. Yes.
Okay, but what do you mean not complete?
They're insufficient. Yes, that's right. Yes, that's what I'm saying. Right. And the reason is, in order to express them properly, requires a radical move. You have to change the way in which logic is done so that the proofs become objects of the theory. And then you can formulate logic properly. And this is what Brouwer was saying back in the 30s, that logic is just a branch of mathematics, whereas everyone up to that point was saying you derive mathematics from the principles of logic.
Just to make sure I understood, so you're saying that if you have some intuitionistic logic for which you define the rules for
Yes, you will be able to, but the conventional formulation will not be, as they say, locally sound, locally complete. That's the point. Okay. They don't fully express the inversion principle that the introduction and eliminations are inverses of one another. And in order to express it properly, you must have proofs as mathematical objects. Okay? Yeah.
This is what it is, because you said that we can give a computational meaning to classical logic expressed as the form of proof by making continuations. So you could derive a similar form to classical logic. The change you're speaking about is not moving from classical to futurist, because it's from making any of this logic in proof theory. Because in type theory, yes.
Yes, exactly, yes. I agree with that. I'm trying to make the argument over and over that really the subject matter is type theory. Okay. And people have approximated type theory in various ways, like more traditional formulations of logic. Now we understand that it should be understood, that should be viewed as just a branch of type theory.
A lot of reasons that people do not like the action choice is that it implies unintuitive results. But some of these unintuitive results, such as the Harper paradox, if we look at the proof, we'll see that they're pretty constructive other than an application of the action choice.
Right.
So does this mean that the Harper paradox holds constructive?
I'd have to think about that. I don't know the answer to you straight off the top of my head. Good question. Other questions? Yes.
I think your third remark on what was going on behind the scenes was that secretly these functions are continuous functions between spaces, right? These functions were continuous functions using topological spaces. Could you explain maybe a bit more in depth why that's easy for doing acting of choice?
Oh, I just wanted to point out that there's something even more. I was trying to make the analogy that the idea is that not only is there a functional dependency here, but I can interpret it also as a continuous dependency. And it still works, in which case this will be a continuous function between topological spaces. And I'm not going to develop that idea further right now, but it will come up later in the course of the summer school. Okay. All right. I just wanted to be provocative and say, here are some things coming, okay, that are very important to what we're doing. Okay. But it's all in the idea that proofs are objects of the theory. That is the most important idea. Okay? And that's the central thing that distinguishes my view, that distinguishes type theory, and that makes many, many, many things possible. So, and we'll look at other applications of these ideas as we go along. Okay? Okay, let me get my bearings. And figure out where I know what I wanted to do next. Okay. So before we go to lunch, what time am I supposed to finish? Somebody? Now. Okay, I can pick this up next time then. What I want to do is I was going to now introduce the natural numbers finally. And the reason is that I kept delaying it because to do it properly requires the apparatus of dependent types, and so you have this pedagogical problem about where do you start. So I'm now actually in a good position to define the natural numbers. So what I will do is I'll do that, and then I will come back to these issues of equality, and then I will talk about what are called growth-indique universes and universes of propositions, and go from there. Okay, so that's what's going to be happening. Okay.